Hello folks, and welcome to the channel. And in this episode we're going to look at the ECU of a car. I'm quite sure you've heard the term "my car is chipped." Well, after this video you will know exactly what this is. So before we dig into the ECU, it might be a good idea to look at a combustion engine. What is it made of and how does it operate? The engine block is either made out of cast iron or light material. It has the bores inside, and in this case we're looking at a 4-cylinder. Inside the bores you will find the pistons. The crankshaft is driving the pistons and is mounted underneath the engine block. It has multiple bearings and a sprocket for the distribution and timing. The pistons are typically light material and connected with the conrod to the engine. The crankshaft is mounted underneath the engine and pistons connect to it, as I said before, with the conrods. We also have what we call a camshaft, and the camshaft can be on top of the valves or below. The cylinder head is on top of the engine block and houses the valves to allow gases to come in and out of the cylinders. The camshaft is timing the valves, and the camshaft by itself is timed by the crankshaft. We also need to have a fuel system. That could be a carburetor or an injection system. It doesn't really matter here. We need to cool the engine with a cooling system, so we have a water pump, thermostats, fans, radiators and temperature sensors, and we have to have an ignition system to ignite this air-fuel mixture. That could be very traditional, it could be electronic. The bottom line is we're going to need a spark plug and we're going to need a system to ignite that fuel mixture. It doesn't really matter if it's classic or electronic. And then finally we need an oil system to grease and oil the engine. And that is it. So as you have seen, a combustion engine is very simple. Now of course there are many different variants on how the engine can be built, but the principles are always the same. But let us now talk on how that engine is operating. So first of all, we have the pistons that are sitting inside the cylinders. And the pistons are moving up and down in the cylinder. And if we're talking about a 4-stroke engine, we basically can define 4 strokes. An intake stroke, a compression stroke, a combustion or labor stroke, and then finally an outlet stroke. But how does all that work? Well, assume that the piston is in the top dead center and that the crankshaft is rotating. The piston is going to come down and it's going to create a vacuum. If we now have the inlet valve open, we can let the air-fuel mixture stream into the cylinder. And while the piston is descending, at some moment in time, it's going to reach bottom dead center. And by that time, the entire cylinder will be filled with a combustible mixture, an AFR, air-fuel ratio, and that's typically around 14.3 parts of air and 1 part of fuel. We also call this the stoichiometric value, meaning that is the best mixture for burning the fuel in the most efficient way. Anyhow, our piston is now at the bottom dead center, and this movement where we're getting the air-fuel mixture into the cylinder, this is what we call the intake stroke or the inlet stroke. Now the piston is at the bottom dead center and our crankshaft keeps rotating. It's going to push that piston back up. And while the piston is being pushed up, we have both the inlet and the outlet valve closed. So basically we go in to compress this gas, this mixture. And when the piston is at top dead center, we have a high compression on that mixture and we go in to ignite that mixture at that moment in time. And a few degrees before top dead center, we go in to ignite this mixture. And there's a good reason why we do that, because the burning rate of an air-fuel mixture is not immediate. It takes a little bit of time before the peak arrives, and we want to have this peak of the explosion just after top dead center, because if we have it before top dead center, you have what we call ping. An exploding mixture expands. As both valves are closed, inlet and outlet, the piston is going to be pushed down violently with a lot of force. And how much force, that depends really on where this burning peak is, but also on the composition of the air-fuel mixture itself. So the piston is now moving down under that force of the explosion, and it forces the crankshaft to rotate. This is the only stroke, which is the labor stroke, which is pushing the crankshaft around. The intake stroke, the outlet stroke, and the compression stroke are all labor actions for the crankshaft to move the piston around. But now we are in our labor stroke, and the piston is now going down. It's going to reach bottom dead center, and by now the force of that explosion is basically nil, and it's time to get rid of the combustion gases that are still left in that cylinder. And this is what we're now going to call the outlet stroke. And now the outlet valve will open up, the crankshaft keeps on running, and it's going to push the piston back up, and the piston will push out all the fumes and exhaust gases through the exhaust manifold. When the piston reaches top dead center, the outlet valve is closing, and we can start a complete new cycle. Now, as you probably will realize, the valves have to open up at the right time and for the right amount of time. The same thing is true for your ignition. The spark has to arrive at the right time. Those timings are very critical for the efficiency of the engine. But also we need to make sure that we have an air-fuel mixture which is right. So all this timing must really be controlled. Now we do know that the crankshaft is linked to the camshaft, because the camshaft is driving the valves, typically with a chain or even with a belt. Now in the old days, all this timing and all these mixtures and ignition moments were all regulated with distributors and vacuum lines and carburetors. If you had a carburetor, you probably had an idle circuit, you have a progression circuit, and you had an acceleration circuit and a cruising circuit, or the main circuit. All that had to be jetted. That would control actually your air-fuel ratio. In terms of ignition, well, we had a distributor. We had bob weights inside that would advance or retard the ignition, and we would also have a vacuum. All that would make sure that we have proper valve and ignition timing and the right mixture. Now in more modern cars with an ECU is what we would call a microprocessor, specially programmed to drive and control that entire engine. So the ECU plays a vital role in defining the air-fuel ratio, when the fuel is injected, how much fuel is injected. It also plays an important role for the ignition. How much advance? Do I retard? Do I advance? And it may even play a role on your wastegate on your turbo, and it may play a role even on modifying the camshaft, because we do have today variable camshafts, the VCCs. So all of that is quite interesting, and the ECU, which is nothing more than an electronics microprocessor which is programmed with a fuel map, needs to understand what the status of the engine is and what is required by the driver or the engine, and then adjust the signals towards all the components, the ignition, the injection, to make sure that the engine is reacting in the proper way. And this is a very complex matter, and that is the role of an ECU. So if we do a little recap, the main purpose of an ECU is to control and manage the engine in the best possible way for a given situation. Now you can imagine in the winter when it's cold and you need to crank up the engine, you need to have a more rich fuel mixture. Typically in the old days we would pull the choke and then we would start. When the engine is warm, we can deal with a leaner mixture. The reality is with an ECU we don't have a choke, so the ECU will need to know what the temperature is. It needs to know that it's a cold start, so it can adjust the AFR, the air-fuel ratio, and it can adjust the timing of the ignition. Now let's talk a little bit about the air-fuel ratio, and we will go much deeper into this later on. Cold start requires a rich mixture. Cruising along on the highway without any load on the car, you can drive much leaner. So today we have a lot of environmental conditions imposed upon us by the governments, and car manufacturers need to consider that, and they are programming the ECUs with a fuel map. And a fuel map is nothing more than a table that tells the ECU how much fuel needs to be injected at a given time for X amount of air under certain circumstances. It's a map. And this map is programmed inside the ECU. If you take in your car to a tuning center and you want to chip your car, and now we are to the chipping story, then they're going to change that fuel map. And instead of making it more environmental friendly, it's going to become a little bit less environmental friendly, but you're going to have more performance. You will also have more consumption, of course. But that's what you do when you start tuning your engine. Now, many cars today are sub-optimum tuned by the manufacturers. And if you want to buy a car with more horsepower, the same type and the same model, you can, and you pay a little bit more. And all they do really is putting another fuel map inside. That's what they do. Now, you can change the fuel map in one of those tuning centers. In the old days, we used to take out the chip out of that circuit board, a little microchip. We would reprogram that chip, and typically we call that an EEPROM, with a new fuel map, and then we put the chip back into the ECU. That's what we called the ECU, or the car is now chipped. That's where it's coming from. Nowadays, that is no longer possible, so we just program up with a special programming device the memory inside the ECU. But keep in mind that in many ECUs today, specifically on production cars, you can't get in anymore. They have it protected, they have it encrypted, there are certificates on it, so you really need a real special tool with licenses and all that to get into that ECU. So is this the end for us enthusiasts? Unfortunately it is. However, you can also buy open ECUs, and an open ECU is an ECU where you have full control of full access, and you can actually load your own fuel maps, and you can manipulate all kind of parameters inside. There are several of those on the market, and Emerald is one of them. It probably runs about a 900 to 1,000 euros or dollars. It's not cheap, but they have all kind of support. So this is something you could do if you wanted to do it, but if you're a novice, I would not recommend to do so. So the ECU has to drive the injectors when they open up and for how long, at the right time. It also has to drive the ignition system. So these are output signals from the ECU. And it's not constrained to just those two. It may even drive your camshaft, the variable camshaft that is, or the wastegate on your turbo, and many other elements like your cooling fan and so on. This is what we call a COP. So this is a coil on plug. And it is actually a high tension coil, and it is controlled and switched to these little pins that you see there. And guess who is controlling this one? There is an output on the ECU that will toggle the current through this coil here, and obviously when that happens, the plug or spark plug is sitting in it. What's going to happen is that we get a spark as soon as the ECU pulses that line there. And these pulses are typically PWM, pulse width modulation. But this was just an example on what the ECU has to drive. And here we have another typical example of a device that needs to be driven by the ECU. This is a solenoid which is going to regulate the amount of oil flowing through this part here, and it's used to adjust the variable camshafts. And you will see that we have right here a connector with pins, and this is where the ECU will steer it. But then the question is, how does the ECU know what to drive? How does it know in what state or condition the engine is, and what we as a driver demand from the engine? Maybe we are flooring the pedal. How does it know that? How does the engine know what the position of the camshaft is? How does it know what the engine temperature is? How does it know what the position of the crankshaft is? And it needs to know all that to make a decision to dose the right amount of air and fuel, and to dose the right amount of advance on the ignition system. And it does that through the use of input signals. And the input signals are sensors on your engine. You have, for instance, an oxygen, an O2 sensor on the exhaust manifold. People call it sometimes a lambda. It will measure the amount of oxygen left in the exhaust, so it will tell the ECU how well the burning process is. In other words, the ECU can look on the values of that and determine what to do with the air-fuel ratio. And you can see there's a cable on it and it goes back to a plug, and that's an input signal to the ECU. You have an air temperature sensor, you have a engine temperature sensor, you have an oil pressure sensor, you have an RPM sensor, you have a crankshaft positioning sensor, you have a camshaft positioning sensor, there is a throttle positioning sensor. There's a lot of sensors in the car of all different types, and in the next episodes we will start to look at each one of them. But all these sensors are in one way or another way providing information to the ECU. These are all variables, and the ECU will use the fuel map. It will look on the variables and adjust and interpolate the fuel map, and then make the right decision on what it has to do in terms of air-fuel ratio, how long the injectors have to be open and at what time, and also how many degrees advance it has to give to the ignition and for which cylinder. It will have all that information. This is a mass airflow sensor, and basically it's going to provide information to the ECU how much air mass is flowing through the intake. There's a little heating element inside, and when air flows through it, it's going to cool it down, and then you have kind of an effect on the resistor, which is changing its resistance on temperature and so on. But we talk more about this once we're going to get into great detail on all these sensors and how you can test them out. But of course, that is not the only thing the ECU has in output and input signals. There is something else. It's information. You know, when we sit in our car, we have a dashboard. We want to see the RPMs. We want to see the engine temperature. We might want to see the oil temperature and the oil pressure. We might want to see fuel consumption. We might want to see the alarm light. And here you see an example of the warning lights that we have on the dashboard. And one of them is the engine failure. Of course, that is not the case right now. It's just a self-check. So there is an output on the ECU that provides the dashboard with all those indicators for us as humans to look at. So now we have output, we have input, we have information, but we're missing one thing. We certainly want to have diagnostics. We want to be able, as a human, to talk to the ECU, to check it out, what alarms we have on it, what is going on with the engine. We want to read out things. And therefore we have a human interface, and this is the human interface right here, this little cable. And some of you may recognize this cable. This is an OBD2 interface. This is the OBD2 plug that you can plug into your car, where you can read out information. Now some cars have a proprietary plug, but normally and legally there should be a common plug like this with different protocols on it. So it's not because you have the correct plug that your box, your diagnostics tool, can actually talk to your ECU. There are different languages between the ECUs and the testers, and it all depends on the ECU which language it's want to talk. And when I say language, I mean it's a protocol, and there's about 4 or 5 different protocols to communicate over. One of them, of course, is also the CAN bus, but I'll talk about the CAN bus most likely in another video. That is not important right now. You will find a socket typically underneath your steering wheel somewhere. That's where it's supposed to be. And with this connector, you can actually connect up a diagnostics tool that I have here, and it comes in many different flavors, and you can actually access your ECU and read out a whole bunch of stuff. Now there are pages on that ECU that you won't be able to read because it is proprietary. But there are a lot of pages that you can read and do things with. You can read things, you can set things, you can test things. It all depends a little bit to what you have access and to what not. Now, although the OBD2 book, I call it, is standardized, what car manufacturers must provide, of course, many of them have special things, proprietary things, and for that you're probably going to need a special tester for that purpose. I mentioned to you already briefly that the ECU is sending out output signals in the form of pulse width modulation. And I just want to give you a little example of what PWM is. It is not very complex. It is just a variable pulse that will determine how long an injector is open and at what time, and what is the time in between the openings. And for the same reason, the PWM is used for the VCC, which is the valve control for the variable camshaft, and at the same thing is valid also for the control of many other elements, such as your ignition system. So here you see a typical PWM signal, whereby the pulse is having a certain width and the distance between the pulses is also different. So two things can happen. The ECU can increase the pulse width or decrease it, but it can also affect the time in between them. So we talk about a duty cycle if this pulse is getting bigger. So now let's see what happens if we give it a bigger duty pulse. And let's say we go to 80%. And you see immediately the signal changes. So now we have a very long pulse going up, and that high pulse, that is the opening of the injector, for instance, for a long time. And then obviously it's closed for a very short time, which is the lower bar. Now that's not the kind of pulse you would expect, but this is what we mean PWM signal. So now we just modified it, and now we have another signal. Now the injector is shortly open, but then it stays closed for a longer time. And I'm just trying to demonstrate what pulse width modulation really means. So folks, we've come to the end of this video, and I hope that you enjoyed it. I've kept things as simple as possible, and it is a good thing for a start. But in the next episode, we're going to dig into the sensors and how they work, what kind of signals they provide, and how you can actually test them out. And in the last video, we'll be talking about an open ECU and on how you can actually deal with the fuel maps or how you can set certain things. Thank you for viewing. Bye-bye.